So far, we've only had one way to solve problems, and that's use Newton's second law, where sum of the forces is mass times acceleration. But there's another very important way to solve them. It's really pretty much the only other way we'll learn how to solve problems in intro physics, and it's got to give us the same answer, but it's a different way to do it. This involves principle of conservation of energy. Force is a vector, but energy is just going to be a scalar, which makes life easier. The units of energy are going to turn out to be kilogram meters squared per second squared, and it comes up so often that it has its own name, and it's a joule. Capital J is a symbol. The idea of conservation of energy is the same as what you hopefully do with your checking account or bank account or whatever. It's just keeping track of additions and subtractions, and those always have to balance. So we haven't defined total energy, but what this conservation of energy says is the total energy of an isolated system doesn't change. There's a related quantity called work. It's measured in the same units, but the way we typically use it is we use work if we're talking about a transfer of energy from one type to another, one place to another. We use energy for the amount in a particular place. Financially, this would be like energy would be like the balance, and work would be like deposits or withdrawals. If you open an account with some amount of money X, you should be able to account for everything coming into or going out of the account over a month. You should never have money just disappear randomly or appear randomly. Once we knew, when we look at the way to solve these things with forces, once we knew some of the forces is MA, the rest of the stuff we did after that was basically identifying different types of forces like gravity, tension, friction, normal force, and then work problems. Our guiding principle here, our big idea, is that the energy at the start of a problem is equal to the energy at the end of a problem, or the energy anywhere in the middle of it. So what we're going to do now is figure out some types of energy and then work problems with them. So the first kind we're going to look at is kinetic energy. This is energy that any moving body with mass has. There's going to be a different kind of kinetic energy associated with rotating things, but that'll be a while. That's a few chapters down the road. When we get to that, we'll call this stuff that we're about to do translational kinetic energy, but since this is the only kind we have right now, we can just call it KE. We define it as 1/2 mass times velocity squared, and for example, if we have a 5 kilogram rock moving at 30 meters per second, we can do the math and figure out that that's 2,250 joules of kinetic energy. But there are other kinds of energy, and the next one we're going to look at is gravitational potential energy. Potential energy is something that an object has because of its position. So if we move it higher or lower in a gravitational field, its potential energy will increase or decrease. Springs also have potential energy because of their position. If we separate the two ends of a spring very far from each other, we're going to store a lot of energy there. We'll deal with springs later, but for now we'll just look at gravitational PE. One way we could figure this out is we could ask ourselves, how high above the ground could a rock going at 30 meters per second climb? We already know from our kinematics chapter that the max height is v squared over 2g. We could rearrange this a little bit into a couple of different forms and eventually put it as gh is 1/2 v squared. We can multiply the sides of an equation by anything as long as we do the same factor on both sides. And we're going to use mass for that factor. When we do that, we get mgh on the left and 1/2 mv squared on the right. We know that 1/2 mv squared is a kinetic energy. So what this is telling us is the potential energy is of the form mgh. When the rock gets to the top of its travel, its energy is now entirely potential, not kinetic at all. To figure out this value of potential energy, though, it depends on where we set our zero, where we start measuring. Typically, the smart thing to do is going to be to make h equals 0 at the lowest point in the problem. For example, though, if we were on an airplane and it's flying 9,000 meters above the Earth and we've got a suitcase in the overhead bin, we could ask, what is its potential energy? If we measure from the ground, we'll get a huge number. mgh is 882,000 joules. If we measure from the plane's floor, though, the height's probably only about 2 meters, we get 196 joules. Which one we use depends on where the suitcase can end up. If it's just going to fall out and land on the floor, 196 is what we would care about. If it can conceivably get out of the plane and hit the ground, then the 882,000 is important. So for an example, let's look at a 2 kilogram block at the top of a frictionless inclined plane. We'll say it's 30 meters long and the high end is 15 meters above the ground. After the block slides 10 meters along the plane, 1/3 of the way down, how fast is it going? And there's two ways to do this. We can use Newton's second law, find the acceleration and then the kinematic equations, or we could do the new conservation of energy method. We're going to do both and see that we get the same thing. So first of all, we look at the geometry of the problem and we realize that we can find theta by taking the arc sine of 15/30 and we get 30 degrees. So that's our angle here. We've already done this, and we know that for a frictionless plane, an object sliding down it will accelerate at a rate of g times sine theta. There is, of course, no acceleration perpendicular to the plane. It's all along the plane. So A is 4.9 meters per second squared here. If we use our kinematic equations, we assume it starts at 0 velocity. The distance it slides is 10 meters. We do the math and get 9.9 meters per second. And this isn't a particularly horrible problem. Although keep in mind we did already have this, we didn't have to find this all over again because we've done it in a previous chapter. What about if we do this with conservation of energy? The way we do it is at each point we list every kind of energy that we know of and how much the object has of that kind of energy. So at the top we have mgh initial plus 1/2 mv initial squared. This is our gravitational potential and our kinetic energy at the start. Our initial height is 15 meters off the ground. The 30 has nothing to do with anything at this point. We just want to know the height straight up and down. Initial velocity was 0, so this term is actually going to fall out. It won't really have any kinetic energy at the start. If we go 10 meters further down the plane to our final position, we'll have, again, mgh final and 1/2 mv final squared. V final is what we're trying to find here. We can find the h final if we realize moving 10 meters along the plane gives us a drop in height of 10 sine 30, or 5 meters. So if we started out 15 meters above the ground, we finish 10 meters above the ground. Conservation of energy says the energy at these two places has to be the same, so we get mgh initial is mgh final plus 1/2 mv final squared. Remember, we have no v initial. We don't really need to know the box's mass. If you look, it'll cancel out, and we get something like this. And then we also see why we were able to pick our origin for potential energy in the airplane and suitcase problem. Really, all that matters is change in height. So g delta h is 1/2 v final squared. So we plug this in, and we get 9.9 meters per second, which we got the other way. And you might even feel like the other way was easier than this. However, what if instead of that nice flat inclined plane, we had something like this, a roller coaster with this very weird pattern of dips and jumps? You would not want to do this with the force method, because the problem here, while it's exactly the same as for the energy method, it's exactly the same as what we did before. All we need to do is square root of 2g times change in height. In the force case, we would have to break this complicated, messy curve into essentially an infinite bunch of line segments, each of which is straight, and treat each one like an inclined plane. So we'll have a different theta for each one, and we'll have to do that kinematic equation for each one. And only for the first one will V0 be 0. For the rest of them, we'll have to keep track of the accumulated velocity as it falls. If we have an analytic formula for the shape of the curve, if it's something like a sine or a cosine, we could do it with an integral, but it wouldn't be a lot of fun. Without that, it's almost impossible. So what we're going to see is we can get the same results with either forces or energy, so there's going to be a connection between them, and that's the work-energy theorem. This says that we can relate work, force, and displacement with this integral. Work is the integral of the dot product of the force and the displacement from the initial to the final positions. You notice here you get the largest work if force and displacement are in the same direction, since we have a dot product, and theta is the angle between the two. When we first talked about vectors, the example I gave here was someone standing behind a car pushing versus someone leaning in the window pushing on the steering wheel, and the person behind the car will do more work for the same force. For example, if we want to lift a 10 kilogram rock from the ground where h equals 0 to the top of a 3-meter shelf, how much work do we do? We're going to lift at a constant velocity and it can be arbitrarily slow. So the force we exert will essentially be exactly the same as gravity's, mg. The displacement is 3 meters. The angle between force and displacement is 0 because they're both pointed up. Cosine of 0 is 1, so the work we do is mgh. This is where we get gravitational potential energy. Because gravity is conservative, that means we don't care about the path taken, only the initial and final points are important. If we ask about the work done by gravity instead of by us, we get a different answer. The force is still mg, but it's now downward since that's the direction gravity acts. The displacement doesn't change because the block is still moving up to the top of the shelf. So theta is 180, cosine theta is -1, and the work done by gravity is negative mgh. This is again just like the way money works. You consider your water bill a negative for your checking account, but it's a positive for the water companies. You'll sometimes see the work energy formula written as work equals force times displacement. This is only exactly true if force and displacement are in the same direction and the force is a constant. Otherwise, you need the integral. And to get a little better idea what the path independence means, look at these two ways to put the ball on top of a shelf. Path A is the very simple one. mgh is easy to calculate because we know the force and the displacement. On the vertical segment, we get mgh. We get nothing on the horizontal segment because force and displacement are perpendicular. This long, complicated mess, the green B path, B1, force and displacement are parallel, so we're doing mg times that little segment of distance there work on that piece. But here on B2, we're doing no work. And on B3, where we're moving down, we're actually getting energy back from the system at that point. So this can only happen if we have this path independence. That means we have a conservative force. So just the beginning and the end are the only things that matter.